Okay, so this is the design for our MEAM 248 heat engine. As you know, the goal of the project was to use this piston and use its motion from heating and cooling to store potential energy. When we started reviewing previous designs for inspiration, we saw a design we really liked. We called it the double ratchet. Basically, the idea is you have some kind of arm that rotates, two more arms attached to it on either side that go up and down with the arm. One goes up when one side of the arm goes up, and one goes down, and they ratchet into a sliding rack that climbs up and down. And well, it only climbs up because as you move up one side goes up, one side of the ratchet goes up, and the other side of the ratcheting arm sort of falls out of the ratchet as it goes down. And it locks in on the way up because of the notch and the ratchet system, and climbs all the way up. This way you can utilize the up and down motion of the piston to raise the rack on the up and the downstroke, which is something that's important for not wasting energy. So when we decided we wanted to go with this design, I started with a sketch like this to figure out the linkage geometry and the lengths of everything we wanted, because there's a little bit of linkages involved, and there are a few considerations. The considerations are the length of this lever arm, center to piston, and the lengths of these ratcheting arms, because one of the things you need to keep in mind is these are two force members the way we've designed them with a bearing here, so keeping them as vertical as possible is more efficient. And as the further up you move this along this arm, it increases the amount of up or down movement you get with each piston stroke, as well as the length of this arm, because if it's out here, the piston is moving up and down the same amount, but you have less angle change here. So I played around with a few linkage distances, and this was the one I came up with that seemed to give a good balance of up and down movement and keeping these vertical. And also these ratcheting arms, they can't shift past vertical because then they'll fall over. We saw some teams with rubber bands holding these together, but the reason we didn't go with that is because on the upstroke, the arm that's going down needs to freely move out. And if there's a rubber band holding them together, it will actually push down the rack. So we carefully designed these teeth so that when you go up, it locks into place, and when it goes down, it falls out and keeps the arm vertical. So that was the idea. We also made everything acrylic, the sliding surfaces acrylic to reduce sliding friction, as well as bearings in our rotating sections. Anyway, so this is how it looks when we actually built it. This thing attaches to the piston, it rotates to reduce friction, and this arm you can change lengths because you can easily switch it out here. So if you want a longer lever arm, because we find out there's too much friction, we can change it. But basically the idea is it moves up, one side locks and the other side swings out, and the whole thing climbs up. And the bearings here make the friction relatively low, as low as we can make it.
Now we're going to take a look at the thermodynamics of our heat engine through a PV diagram. The initial state of the system is in the cold water bath while the piston is compressed. In the first step, the air is heated by placing the can in the hot water bath. Volume stays constant, so pressure increases as temperature increases. This process does no work for the system. Once the pressure inside the system counteracts the external force on the piston, the air begins to expand at constant T. Pressure and volume at constant temperature have an inverse relationship, resulting in a bowed line. This process is an adiabatic expansion that produces positive work for the system. Once the piston reaches its maximum volume, the can is placed back in the cold water bath, resulting in a decrease in pressure. In this case, pressure and temperature are directly related at constant volume. This process does no work for the system. Once the internal pressure of the air reaches a value less than the external force on the piston, volume begins to decrease at constant temperature, resulting in another bowed line on the PV diagram. This process is an adiabatic compression and produces negative work on the system. The total work done by the heat engine can be represented by the area under the curve. Now we're going to take a look at Newton's law of cooling. The important idea is that the rate of temperature change of a body is related to the difference between its temperature and the ambient. As its temperature gets closer to the ambient, its rate of cooling or heating slows. The majority of the temperature change results within the two red lines on the graph. In the case of the heat engine, the ambient temperatures are the cold and hot water baths, and the body being cooled is the air inside the system. This led us to believe that it's better to change the can from bath to bath more rapidly than waiting for the system to fully reach its minimum or maximum temperature. Because of this, the work done per cycle of our heat engine will be smaller, but there will be more cycles completed, leaving us with greater total work after 5 minutes.
So in order to find the optimal mass of our heat engine, we first needed to draw a free body diagram of the piston and look into the forces acting on it. And by using Newton's second law and summing the forces into zero, we'll be able to find the pressure acting. And we can see that the pressure acting on the piston will equal to the weight over the area plus the atmospheric pressure. And we can also find the final volume by using the ideal gas law and plugging all of that into the work equation. So we know that the work from the PV diagram will equal to the difference of the pressures times the difference in the volumes. And after plugging all the previous equations, we can find a relationship between the work and the mass. And after plotting this function into MATLAB, the plot of the work versus mass would look parabolic, and the maximum work achieved would require a mass of 1.4 kilograms, but experimentally we needed to use a mass of 200 grams, and this is due to the stability of our design. And the height achieved at this mass would be 0.635 meters. So the potential energy would be 1.2 joules. But theoretically, after finding the final volume that the system can achieve, the work would be 0.57 joules. But however, the volume is constrained by the volume of the piston, which has a maximum of 0.0011 meters cubed. So experimentally, the work would be 0.093 joules, which is significantly lower than the theoretical work. So to find the number of cycles that we need to achieve for each work, we know that the theoretical number of cycles would be 2 cycles, but experimentally we would need 13 cycles to achieve this potential energy. And this matches the number of cycles that we have actually done in the lab.
During the testing of our heat engine, we ran into a few unexpected problems. The first problem was that the mass was placed at the top of the rack, which began to tilt as its height approached its maximum. One way we could have fixed this is by attaching the weight to the rack by a string and have it hang below the heat engine. The second issue we ran into was that the ratchet arms were not constrained well enough, and they would disconnect themselves out of the notches of the rack. The way we fix this is by placing strips of paper on either side of the rack to constrain the lateral motion of the ratchet arms and keep them connected to the teeth. Despite these issues, we still performed well during engine testing. During the first run, we raised a mass of 196 grams, up 32.3 centimeters, in 3 minutes and 50 seconds. This was to get the maximum potential energy out of one rack's motion. The second test was aimed towards achieving the greater total distance, broken up into parts. We reset our rack 3 times to its initial height, achieving a total distance raised of 63.5 centimeters. The total potential energy stored by the heat engine was 1.2 joules. In both tests, the hot water and ice water had average temperatures of 80°C and 2°C respectively. This influenced our results versus expected, as in the calculations, it was taken that each bath was at constant temperature of 100°C and 0°C. Hopefully after watching this video, it's clear on how we approached our heat engine project. Thanks for listening.